over to you, Chris.
Thank you. Okay, so I'm just going to share my slides with you. Please let me know when you can see them.
Yep, that's
Super.
good.
Super.
Wonderful.
Okay. So this talk is about a European mission that you may have heard about, which will be launched in the next couple of years to go to Jupiter. And it had sort of a bit of a tortuous journey to get to where it is now, that I'm going to sort of talk about, sort of like the politics and history of how some of these things get started. So that's what we're going to be talking about, this mission to Jupiter, and particularly to its largest satellite, Ganymede, the largest moon in the solar system. So we're talking about a mission to the giant planets, and the location of these bodies in the solar system is sort of a big part of this mission, because part of this mission is about extending our understanding of what it means to be habitable, what it means for a world to be habitable. And you've probably got this notion. Let me just find my pointer here. This notion of, well, we have this Goldilocks zone. So the Earth is just close enough to the sun so that we're kept warm, so we're not too far out where it's too cold for life, and we're not too close where it's too hot for life. We're just in this Goldilocks zone. We're in this sweet spot here. But some of the ideas that have led to the JUICE mission are about, well, couldn't there be other environments that are conducive to life further out in the solar system? So we're talking about some of the satellites of the giant planets, particularly the satellites of Jupiter in this case. But this has also been fed and reinforced by some of the discoveries at Saturn from the Cassini mission. So there are a whole set of different science goals here to do with the giant planets, but one particular focus is about this question of what does it mean for something to be habitable, or put another way, might there be a whole plethora of different types of habitable planetary environment in the solar system, and of course beyond our solar system. So this sketch shows Earth, the Moon, Mars in correct proportions to the satellites, the main satellites of Jupiter and Saturn. So Mars is obviously a fair size smaller than the Earth, but then Mars isn't so small compared, so much bigger than some of the satellites of the giant planets. So the four here are the Galilean satellites of Jupiter, the innermost Io at the top there, through Europa, Ganymede and Callisto. And then compare those with the main satellites of Saturn, obviously sort of crowned with the giant satellite Titan, second largest moon in the solar system behind Ganymede. And these bodies, they're bigger than the moon. They are competitive with Mars for size, and they're also big. Ganymede's bigger than Mercury, so we're talking about substantial worlds here. So these are the bodies where we're opening these questions about habitability. We're also talking about habitability at Titan. People talk about it for Titan and Enceladus. That's a different talk though. But here we're talking really about, well, actually really about the bottom three here. As I'm going to talk about, Io is a very unpleasant place to holiday on, but Europa, Ganymede, and Callisto may harbour places where it's more conducive to life. So what is the JUICE mission in a nutshell? What is this thing about? What is this mission about? This €1 billion plus mission to Jupiter? Well, it's about exploring the emergence of habitable worlds around gas giants. So here we're focusing on Jupiter, and so one of the headline goals for the mission is to characterize Ganymede, Europa, and Callisto, these three Galilean satellites, characterize those as planetary objects. So as moons, as bodies that exist in the solar system, characterize those as objects. You know, what are they made of? What is their internal structure? How warm are they? What are the layers that are inside them, and so on. So characterize them as planetary objects and also as potential habitats. So characterize them as, could these be places where life could exist? So that's less so around the question of could astronauts survive there, but more about pushing the boundaries of where to look for life and what the markers for life. Not looking for life, but trying to understand the question about where should we be looking. So that's what this is what this mission is mainly about. The other headline is to explore the Jupiter system as an archetype, what they call an archetype for gas giants. So what are the sort of the fundamental things that go on in a giant planet system? You know, we look at the giant planets, Jupiter, Saturn, Uranus, and Neptune. We see a variety of of common features. These worlds have active atmospheres. They have probably have solid cores at the center of these fluid planets. Jupiter has a very strong magnetic field. Uranus and Neptune have quite odd magnetic fields. All four of the giant planets have ring systems. They all have this array of natural satellites. Some of them we would categorize as regular satellites, so they have approximately circular orbits, approximately in the equatorial plane of the planet, and then they've got these collections of irregular satellites that are probably captured solar system bodies, but these worlds are in quite eccentric orbits around these giant planets. They may be in quite inclined orbits around these planets. So these giant planet systems are sometimes refer to them as solar systems in miniature, and they sort of harbor all this very, very interesting and complicated interactions between different components of the system. So the other sort of headline for JUICE is to go and look at Jupiter and try and see what we can learn in general about gas giant planetary systems. What can we learn that we could perhaps apply to Saturn, or possibly even to Uranus and Neptune, and to other giant planet systems that we are starting to discover around different worlds, different stars in the galaxy. So when we sort of talk about how these missions are structured, what happens when and so on, and that's what we call the mission profile. This is a slightly old schematic now, but it illustrates the general idea. So the launch, it was at the time of this when this was drawn, we were talking about a launch in 2022. I understand it's been pushed back a little bit, but that's the baseline. Arriving at Jupiter in January 2030. And then once we're at Jupiter, we have this procedure called JOI, that's Jupiter Orbit Insertion. That's the maneuver where engines are fired in order to slow down the spacecraft to be captured by Jupiter's gravity. And then once we've had JOI, we have each of these perigerbs, so each of these closest approaches of the spacecraft with Jupiter. And so you see these occur fairly regularly through the mission. And we have a number of different flybys of different satellites during this mission. So we're going along in time from left to right here. So, we just after Jupiter orbit insertion, we have a flyby of Ganymede. And then we start to get these repeated flybys of Ganymede. We see Europa twice. We have quite a number of flybys of Callisto. And then in September of 2032, we see this long solid bar here, and that's not lots and lots and lots of encounters with Ganymede. It's one long encounter with Ganymede, because this is where JUICE will go into an orbit insertion maneuver to go into orbit around Ganymede. So it will now be trapped around Ganymede. And then we'll have a whole set of orbits around Ganymede studying the planet first in an elliptical orbit around Ganymede, and then it will go into a more circular orbit around Ganymede. And the end of mission will be in 2033, where there'll be a sort of a descent of the spacecraft down to the surface of Ganymede, a little bit like Rosetta did when it descended and finished its mission on the surface of the comet, of its main target. The two things that, two particular aspects of this mission are that Jupiter poses a very challenging radiation environment for JUICE. Jupiter's planetary system and Jupiter's magnetosphere is the host of the strongest radiation belts, planetary radiation belts in the solar system. And so this basically has the capacity to fry the electronics on the spacecraft and also damage the solar cells. And so this is something that the designers and the instrument builders and the even down to designing the operations, this is something that we've had to think very carefully about how to manage. The sketches up at the top right of the slide up here, these show 3 of the earlier designs for the JUICE spacecraft. So back when it had been selected, but we were still working out how to do a lot of things. The European Space Agency had 3 contractors look at how they were going to overcome some of these challenges. How were they going to maneuver the spacecraft in the system? How were they going to power it electrically? What rockets would it need? How would it turn itself to point its cameras at different things? What shape would the solar arrays be, and all of these sorts of design questions and engineering questions. And they came up with these 3 designs, and I believe it's this bottom one that we're running with now. And so you can see how large these solar arrays are. If you've seen seen photographs of the Rosetta spacecraft, so that absolutely enormous solar arrays. I'm going to show a picture of the Juno spacecraft later on, which has got enormous solar arrays as well. And you need these massive solar arrays because the sunlight at Jupiter is 1/25th that near the Earth. So Jupiter is just over 5 astronomical units. Sunlight falls off as 1/r². So the sunlight at Jupiter is 1/25th that near the Earth. So you need huge solar panels to generate the electricity that the spacecraft needs. But you've not only got to consider, well, what is this sunlight? It's 1/25th, okay, that's fine. I know I can make a solar cell that maybe converts 25% of sunlight into electricity, takes 25% of that solar energy and converts that directly into electrical energy. But that efficiency is not fixed in time. I mentioned this radiation environment, and that radiation environment will degrade and damage the solar cells over time, so that efficiency goes down slowly and steadily over the mission, sometimes in fits and spurts if it goes into a particularly radiation hard environment. So the environment around Europa, for example, is very radiation intense. It's better the further out you are. And so, those encounters with Jupiter will constitute quite a large radiation dose for the spacecraft, and that will sort of give you a spike in the damage. So we may see a spike or an abrupt drop in how much electrical power are produced by the solar cells. So they've got to plan for this eventuality, and it's to some extent an unknown, but also how much energy are we going to be able to get at the end of the mission. So you've got to think about not just how much electricity we'll be generating in 2030 when we arrive, but what will be generated in 2033 at the end of the mission. Will we still have enough electrical power to run everything? And that is everything. That's computers. That is heaters to keep the spacecraft warm. That is opening the valves to fire rockets. It's mechanisms to turn the spacecraft around. It's mechanisms to articulate the solar arrays to keep them pointed at the sun. So there's a whole host of things that are being powered on the spacecraft and that need to be kept powered. One of the other challenges in this system is known as planetary protection, and this sort of is a direct antagonist of the radiation problem, and I'll talk more about that later. This comes about because Europa is this very interesting planetary object with this potential for habitability. The question there is, let's say in 1,000 years we have people walking around on Europa, and and maybe we're going down through the surface ice on Europa. We're melting through this surface ice and we're emerging into this ocean world underneath the ice. So Europa we've got good evidence at Europa that there is this shell of ice on top. That's what we see when we look at Europa, but underneath we have this potentially only a few kilometers, below the ice shell. We have this zone of liquid water overlying the mantle, this rocky mantle. So say in 1,000 years, people are walking around on Europa. We've managed to go down through this ice and have a little, some sort of little underwater vehicle, some sort of submarine, a bit like going down to Titanic. And you're down there and you see some sort of fish or you see a dolphin. The question then is that genuine indigenous European life, or was it contamination when Zeus crashed into Europa by accident? Was a spacecraft carrying microbes or life from Earth and to Europa, and that's what was subsequently found.
So that's a bit like Cat from Red Dwarf.
Yes, exactly. Yeah, exactly. So it doesn't have to be fish or whatever. It could just be bacteria, things like that. Even the chemical residue from extinct life. The question is, how did it get there? And so we want to be sure that we haven't deposited anything on the surface. So there are stringent requirements for decontaminating spacecraft before they get launched, and it depends on the target that you're going to. If you're just going to fly a spacecraft around the sun, it's not that critical. If you are just going to orbit Saturn, it's not that critical. If there is a chance that you could accidentally crash on Europa, or you're intending to end your mission by dropping your spacecraft on Ganymede, then you need to have these requirements to cleanse your spacecraft of Earth bacteria and Earth material. So I'm going to come back onto that later on, but that's a challenge. That's been a challenge for the mission. So I mentioned this sort of tortuous journey, and it's been a bit of an evolution, really. So it started out as being called Laplace, and was a mission proposed to the European Space Agency to its L-class program, which was part of Cosmic Vision. And this was originally described as a mission to explore the Jupiter system and its moons. And that eventually evolved into what's called a bilateral. So it was the European Space Agency and NASA joined together, and because NASA wants to explore the Jupiter system as well. And so they sort of both said, well, we both want to do this. Why don't we do something at the same time? Why don't we exploit the opportunity of having two spacecraft around the same planet at the same time? We can get lots and lots of data, and we can benefit from having multiple measurements at the same time. We can have one spacecraft taking pictures of one side of a moon and one spacecraft taking pictures of the other side, or we can take pictures of both sides of Jupiter at the same time. There are all sorts of different science reasons why we would want to do that. And so NASA would send this spacecraft that would eventually go into orbit around Europa, and the European Space Agency would launch something to go into orbit around Ganymede. But there were funding changes within NASA, which meant that they basically dropped this. They decided they weren't going to do it anymore. And so ESA had to decide what to do, and eventually they said, well, okay, we're just going to go with an orbiter around Ganymede. We're just going to keep Ganymede part of this mission, and we'll do a few flybys of Europa to try and retrieve some of that science, but we'll just focus on Ganymede. So just to think a bit about some of the missions that have flown before, I'm sure many of you will know of these missions. So the top left here, this is I believe it's a painting. It certainly looks like an oil painting to me of Pioneer. One of the Pioneer spacecraft back in the 1970s. So Pioneer 10 and 11 flew past Jupiter in the 1970s. First spacecraft across the asteroid belt. Didn't know it was possible at the time. There was a chance we would lose the spacecraft. But they made it through and took some of the first measurements at Jupiter. And then what followed was a whole series of spacecraft. So we have the 2 Voyager spacecraft launched in the 1970s. Voyager 2 was actually launched first. Voyager 1 reached the planet first, hence why it was called Voyager 1. So the Voyagers undertook this grand tour of the solar system. Then after Voyager, the next spacecraft to fly past Jupiter wasn't a planetary mission. It was actually the Ulysses spacecraft in 1992. And Ulysses, if you don't know about Ulysses, Ulysses was the first spacecraft to orbit the poles that go over the poles of the sun. And so it was a mission looking at the sun and looking at the solar wind and the heliosphere. But in order to take it on this path that took it out of the ecliptic and over the poles of the sun, it used a gravity assist from Jupiter to pull it out the ecliptic. And so Ulysses was the next spacecraft to visit. Then we had Galileo in the 1990s and early 2000s. Galileo was actually there when the Cassini spacecraft did a flyby en route to Saturn. And then after that, there was New Horizons, which flew past Jupiter in 2007 on its way out to Pluto. And of course, since then, we've had the Juno spacecraft being in orbit around Jupiter. I'll talk more about that shortly. But let's just talk about Galileo, because Galileo sort of followed on the heels of Voyager. Almost the ink had not, the data almost hadn't got down and all been received on Earth when people were thinking, well, let's go back to Jupiter, let's look more into this really interesting system that we found so much more about since Voyager. And that was launched in 1995, but it was actually it was ready for launch in the 1980s. So this was due to be launched from the space shuttle, and it was due to be launched from the space shuttle in 1986. 1980. It was due to be launched after 1986. But what happened was the Challenger accident happened in 1986, and obviously that grounded the shuttle fleet. So Galileo, ready to be launched, was basically put in storage until it could be safely launched. It wasn't going to be launched from a sort of a typical rocket, because they wanted a really large diameter radio antenna to be able to communicate all of the science measurements back to Earth. And that the diameter of that antenna wouldn't fit in one of the fairings, the nose cone, the top of the rocket. So they had to do something different. And so they decided to launch it from the shuttle, which had a much wider bay. So they put it into storage, and then they resolved the problem with the solid rocket boosters on the shuttle, and it was launched again. But unfortunately, there's a problem in that in order to make this large diameter antenna, they made it unfold like an umbrella. So it was launched in a folded configuration, and this here is basically the folded up umbrella at the top of the spacecraft. And once it was in space, it was designed to unfurl, just like opening an umbrella. And this is this is a computer rendering of what it ended up looking like. And what happened was these ribs on the antenna, they got stuck on part of the antenna, which meant it didn't unfurl properly. And so they didn't get all of the measurements back that they wanted to. And so even though Galileo was a fabulously successful mission and taught us a lot about the system, it was the spacecraft that returned the measurements that gave us the evidence that there was this ocean underneath the surface of Europa. Even though it was fabulously successful, it was still really hampered by this antenna problem. And basically, they couldn't use this antenna at all during the mission, and they had to use some of the smaller antennas that were only designed for emergencies and for communications when they couldn't be pointing the dish at the Earth. They had to use that to send all of the science data back to Earth, which meant they got a fraction of what they actually wanted. So the mission that's currently orbiting Jupiter at the moment is called Juno. And Juno's been there since 2016. It's the first spacecraft to orbit Jupiter that runs on solar power. So all of the previous missions have used nuclear power sources to provide the electrical power. But Juno's using solar power just like JUICE is. And to give you a sense of scale here, these 3 solar arrays here, each one of those is 2 meters by 9, just about 2 meters by just over 9 meters. So these are really huge to provide the electrical power for the spacecraft. And Juno's aims are partly to study the atmosphere, partly to study the interior, and partly to study the aurora of Jupiter. And so this is a picture of the aurora of Jupiter taken in the ultraviolet. And here we can see all of these different structures in the aurora. So you can see we don't have this sort of clean oval shape. It looks more like when you look at this on a polar projection, it looks like a kidney bean. But it's got all of these structures here off to the side. There are these spots, one here. You might be able to discern sort of a little tail here, and there's a tail on this spot here. And these spots are where Jupiter's magnetic field connects with the satellites, where this is with the connection between Jupiter and Io, the innermost of the Galilean satellites. So this is an electrical connection between the moons and the planets itself. But Juno has been flying over this region, looking at the particles that are going down the magnetic field into the atmosphere to produce this aurora. And that's something that JUICE wants to also look at, as well as part of this thing of exploring Jupiter as an archetype for gas giant planets. So let's get into some of the meat about Jupiter itself. So this is a sketch showing a particular phase of solar system formation, and we're looking at the phase of solar system formation where the pressure of the sunlight has started to blow away the disk of gas and dust that the solar system formed from, and you can see the sort of the edge of this disk here starting to be blown away to leave the formed planets behind. But there are lots of questions here about how this process actually worked, and really fundamental questions like, how do you get these dust particles to stick together? So by studying different planets in the solar system, we get a sense of what these planets are made of and where they formed in the solar system. If we think about the formation process, what they're made of tells you about where in this disk they came from, because this disk of material might have had different stuff closer to the star than further away. So the constitution of the planets gives us these fingerprints of what they were made of, where they formed in this disk, and what that disk was made of. So that's one of the reasons for wanting to go out to the planets and look deeper inside them to try and figure out what they're made of. We can look at the upper layers of the planets and that can tell us what molecules are there and so on. But it really doesn't give us that window into the deep interior where the chemical makeup might be quite different or contain other clues. And so we have these pictures of the interiors of the planets. These are it's like looking at it's like peeling an onion. And so we can see these different layers inside the giant planets, and these are all to scale with the Earth. And so we see at the very center of Jupiter, this is what we think is a core of rock and ice. This is one of the things that Juno is there to try and test and determine for sure. But then surrounding this rock and ice core, there's this layer of metallic hydrogen. And this is not metallic hydrogen in the form of a it doesn't look like a piece of steel, for example. It's metallic. We use the term metallic because we're talking about properties of electrical conductivity. And so this hydrogen in the interior of Jupiter is under so much intense pressure that it makes the hydrogen a really good electrical conductor. And that's what gives Jupiter the strongest magnetic field of any planet in the solar system. And this particular state of matter of hydrogen can only be reproduced in the lab on Earth in very, very short bursts. Like, this state can only exist for a few nanoseconds. And they do this in shock tube experiments where they basically have a sample of hydrogen, and they basically fire a gun at it, so it compresses it very, very strongly. So you get these very, very dense, high pressure states. Surrounding this metallic hydrogen layer, we have a layer of molecular hydrogen and helium, just like we get at Saturn. And then all of the activity and rich chemistry that we see on the cloud tops, that's just this very, very thin layer on top. So there's lots of interest in saying, well, what's going on in the deeper regions? And what can that tell us about the formation of the solar system? But these outer layers are really interesting in their own right. And you can see this. I'm going to show a clip of what Voyager saw on its approach to Jupiter just before my first birthday. So I love seeing these sort of landmark clips in our exploration of the solar system. We've got fabulous pictures now, but for some reason for me, the older pictures still give me goosebumps. And on occasion you see these spots. I'm going to keep playing this. On occasion you see these spots coming across the field of view, and these spots are when the Galilean satellites are going in front of Jupiter, giving you these transits. And you see all of this activity in those weather systems, these counter-rotating features, storm systems. Obviously, these different coloured bands that we see in the atmosphere, obviously not seen in colour in this movie, but all of these different colours in the different clouds and the different molecules that are producing them. So the atmosphere is a very interesting and dynamic place. We can see how active it is in this approach video. So the atmosphere is of real interest when we're studying Jupiter. It's it's an atmosphere that's driven differently to the Earth. Now, I mentioned that sunlight is 1/25 what it is at the Earth, and our Earth's weather systems are driven by energy from sunlight. But at Jupiter, there's a lot of energy coming up from the interior as well. So we got some energy coming up from on top, but a lot of energy coming up from the inside. So this is an example of a meteorological system that's driven by energy from underneath rather than coming down from the top. So this is a different way that a planet's atmosphere can work. And so by understanding how all of these moving parts work together, that can tell us about how planets work in a more general way. So we ask questions like what drives these weather systems, and what's the composition, the chemistry in the atmosphere. We have these different cloud decks in the atmosphere, giving rise to these different colors. So we have a cloud deck of water molecules, just like on Earth. But here we have cloud decks of other materials. We have ammonia clouds here. I completely forget what this molecule is. But we've got these different cloud decks at different pressure levels, different altitudes. So what's the vertical structure here? What are these different layers? And how does this radiation-rich magnetosphere surrounding Jupiter, how does that interact with the atmosphere? How much energy does that deposit in these upper regions? The aurora is a signature of energy input into the atmosphere. So how much energy does it put into the system? And that energy is being deposited in this region up here known as the thermosphere, where you can see the energy climb with increasing altitude. So you would expect the temperature to increase as you go down into the atmosphere, like it does in the troposphere. But here we've got something where it's getting hotter and hotter the further away you get from the clouds. And that's a common feature of planetary atmospheres, but this thermosphere is particularly hot compared to what it should be, and that's an outstanding question that we're trying to answer. I've mentioned this magnetosphere a number of times, and so this gives you this is a sketch of Jupiter's magnetosphere. It's like the magnetic bubble that the planet's magnetic field carves out of the solar wind. So the sun's off on your left-hand side, and it flows from left to right, and it gets it's flowing supersonically. So in order to get around the planet, it needs to be slowed down by this bow shock here, this shock wave here, which sort of compresses and deflects this solar wind around the planet itself. And then we've got Jupiter in the center here with all of these magnetic field lines from Jupiter, this extremely strong magnetic field produced in this metallic hydrogen layer. To give you a sense of scale here, the Earth's magnetosphere that we're all sat in right now is just a tiny fraction of this. It would sit quite cleanly down here, almost fitting inside Jupiter. Not quite, but almost. But on the scale of this diagram, the sun is not too much bigger than the pointer I've got going on here. So the sun would be about so big on this figure. And so this is sometimes described as the largest physical structure in the solar system. There are some observations from Voyager after the Jupiter encounter, when Voyager 1 was on its way to Saturn and Voyager 2 was behind it. So there were some observations that suggested that this what we call the tail, the magnetotail out here, had extended all the way from Jupiter right out to Saturn. So if we think about that, that's 5 astronomical units. So that's a physical thing that extends, like you can think of it like a tube or a pipe. And it's this pipe that's 5 astronomical units long, starting at Jupiter and extending to Saturn and possibly beyond. So this is absolutely huge. And one of the comparisons I like to think about is what it would look like in the night sky. And so if, this is just a sketch of just a screen grab from Stellarium, so it's showing Jupiter in the night sky. And if you were to look at Jupiter and you could see its magnetosphere with the naked eye, it would be about twice as big as the full moon, or about the size of the full moon. That depends on the state of that magnetosphere, and depends on the solar wind, because it changes size depending on how hard the solar wind blows. But it's at least of order the size of the full moon in the night sky. So you think about how big Jupiter looks in the night sky, and then how big the moon looks in the night sky. And when you're seeing Jupiter, you just can't see this magnetosphere that surrounds it, but it's there, and it's the size of our full moon. And one of the reasons it's so large is actually connected with the satellites, the Galilean satellites. And so this is one of the pictures from Galileo, and it shows a volcanic plume off the limb of Io. You can see it there in blue, and you can see it in this zoom in. And so this is a volcanic eruption, and Io was the first place in the solar system where we actually saw an active volcanic eruption. Where we actually first saw a volcanic eruption, and this was seen in Voyager images back in the 70s, but obviously then reobserved with Galileo. And once this material, this volcanic material, is ejected from Io in these volcanic plumes, Some of it does not make its way back down to the surface. Some of it does not rain down on the surface. It actually goes into orbit around Jupiter, forming like a donut or a torus of gas around Jupiter. And that material ultimately interacts with Jupiter's magnetic field and inflates the size of the magnetosphere. And so here you can see some images of these volcanic plumes. These are more recent images, and this is from 2007. This is from the New Horizons flyby of Jupiter, and this is one of those volcanic plumes that's been ejected. So what you're seeing here is this is the night side of Io. This is the day side of Io, and this plume is extended about 300 kilometers into space above Io to rain down. And then we can also see all of these dark features on the surface. And these are all lakes of lava. And you can see those if we look at Io in the infrared. So this is a picture in the infrared of Io. This is the warm day side being heated by sunlight. And then these bright spots here, these are all showing us warm regions on the night side. So these are all these lakes of lava that are all radiating a heat out into space in the infrared. And then this bright patch here, this bright patch is that volcanic eruption that we're seeing in this frame here. It's a very dynamic world. And Jupiter is also a very active place because of its gravitational influence in the solar system. So some of you may remember the Shoemaker-Levy-9 collision with Jupiter in the 1990s. And this is a photograph of some of the fragments of Shoemaker-Levy-9 on their way in to collide with Jupiter. And here is a picture from Hubble showing those scars on the surface of Jupiter's atmosphere, where each one has sort of hit one after another after another. And those impacts not just gave you these scars in the atmosphere, they also gave you an auroral signature. And so this is a picture taken from Hubble, and these at the top, this is actually upside down, but here are the dark patches caused by the impact of the comet fragments. And these are magnetic field lines around Jupiter. And you can see at the other end of the magnetic field to the impact sites, these are what we call the conjugate points. You can see bright auroral emissions. So you can see these bright spots that we'll call the feet of the field lines going into the planet. And so that's actually been produced by these impacts in the opposite hemisphere. It's disrupted the atmosphere so much that it's launched very energetic electrons along these magnetic field lines that have then caused these auroral emissions in the opposite hemisphere. So this is over in this hemisphere after the impact. And one of the other reasons why we want to study Jupiter's magnetosphere is this archetype also has a connection in with astrophysics. And that's because Jupiter has this very, very strong magnetic field. It also rotates really rapidly. And so in some ways, Jupiter's magnetosphere behaves a little bit like a pulsar. It also has it accelerates these particles up to very high energies, giving you these really intense radiation belts. And so that's another reason for us to want to go and study Jupiter as a system. So talking about the satellites, which is the main focus of the JUICE mission, just to focus on the Galilean satellites. So I've talked about Io a little bit. These are true color images showing Io, and the yellow colors are there because of all the sulfur compounds from the volcanic eruptions. And you can see these lakes of lava here in dark colors, and particularly these scars on the surface from the volcanic eruptions and volcanic activity. And this volcanic activity is driven by a tidal interaction between Io, Jupiter, and the other Galilean satellites. And what that does is it raises tides in the solid rock on Io. And we're used to tides being raised here on the Earth in the ocean water of I don't know, of the order of a few meters, let's say. But on Io, these tides are raised in solid rock of hundreds of meters to kilometers in amplitude. And so that represents a tremendous amount of energy. And that energy is deposited in the interior of Io and goes to heating the interior and driving all of this intense volcanic activity. But Io also has a magma interior, just like the Earth does. And so one of the signatures of this magma is in how Jupiter's magnetic field interacts with the interior. And there are some new observations from some reinterpreted observations from Galileo that give us an insight into this magma ocean in the inside. So this is a true color image of Europa. So stepping out now, one satellite from Io, and all of these. One of the things that gets everyone interested is all of these crisscross features on the surface, and so that gives us insights into this icy nature of Europa. That we have something akin to plate tectonics in the ice. That we've got these large regions of ice sheets that are separated from the adjacent ice sheets by these regions that can sort of move and rub against each other, and that can allow liquid and slushy material from the inside to well up in the gap between these sheets of ice. And so that's what people get very excited about when they see this darker material. They wonder what that darker material is made of. You know, the people talk about this is this organic material. What is the gunge that colors these gaps and these cracks? Is that somehow a signature of what's going on inside? So this is that return to this picture of the interior here. You know, so we've got this ocean set on top of the mantle, and then this icy layer where we can exchange material between the surface and the lower levels. So we can have material welling up from lower down and material sinking. So we can have this exchange of material between the surface and the interior. And that turns out to be quite interesting for people who are interested in sort of the astrobiological potential for this ocean down here. And one of the reasons they're interested in this is that you've got some chemistry going on here at the ocean floor, where there are chemical exchanges between the rock and the salts in the rock and so on, leaching into the water. But you've also got similar processes going on at the top. And that's because of this external environment that Europa is embedded in. It's embedded in this magnetosphere with these charged particles. There's charged particles raining down on the surface of Europa, deposit material and drive radiation-induced chemistry in the surface layers. And so that is an agent for producing interesting molecules in its own right. So we've got chemistry going on the surface. Let's just skip back. We've got chemistry going on the surface. We've got chemistry going on at the bottom of the ocean. And then if we've got some process then to mix these two things together into some sort of interesting soup, that might be the right chemical constituents that we need to start building more complicated molecules, start to think about things like amino acids, larger organic molecules, things like that. And one of the things that people are very interested in is, and this is partially driven by some of the Cassini discoveries around Enceladus at Saturn, is what does that ocean floor look like? And you know, when we go down to our own ocean floor, when we go down to our own ocean floor, we find lots of geophysical structures. You know, so we find things like these black smokers, these hydrothermal vents, where we have got hot water loaded with minerals being sort of ejected out of the ocean floor into above the seabed. And because it's carrying all of these minerals, they start to form these mineral columns extending up out of the ocean floor. So we have this sort of hot hot water had been injected out of these vents, carrying all of this chemically rich material. And there are lots of footage, you can see footage of these things where they're just surrounded by prawns and other sea life, because they're thronging to somewhere that's warm and that's nutrient rich. That's what makes people very interested about what's going on at the ocean floor on Europa. Is there are there analogous structures there? The main focus of Jupiter is on Ganymede, and Ganymede is the largest moon in the solar system, but also it's the only moon that we know of in the solar system that has its own magnetic field. So it has its own bar magnet, if you like, in the center, just like the Earth does, that produces a magnetic field. And you can, and one of the pieces of evidence that there's something interesting like that happening is in this difference in coloration that you can see here. So you can see that the polar regions on Ganymede at the top here and down at the bottom here, they're a different color to the near equatorial regions. And that's because of the presence of of Ganymede's magnetic field. What Ganymede's magnetic field does is that it protects the near equatorial regions from this radiation around Jupiter, but it can't stop it at the poles. And so the radiation rains down on the poles, chemically affecting the ice, but it doesn't happen in the near equatorial regions. And so if we merge this with a picture of a computer simulation of what Ganymede's magnetosphere looks like, this is Ganymede's magnetosphere embedded in Jupiter's magnetosphere. The white lines and arrows here are representing the magnetic field. And so you can see this magnetic field here protecting the near equatorial regions from all of the radiation around Jupiter. But here in the polar regions, these magnetic field lines connect into that of Jupiter, providing that mechanism for the radiation to sort of flow along these magnetic field lines from Jupiter and then rain down onto the polar caps. And then we even have aurora on Ganymede and Ganymede's tenuous atmosphere at this boundary between where these magnetic field lines connect to Ganymede itself and where they can go off to connect to Jupiter. And this is a picture of Ganymede's aurora in green here and here, sort of hovering around this region here and here. This is taken in the ultraviolet by the Hubble Space Telescope. And then finally, the other target, the other Galilean target for JUICE is Callisto. And to my mind, Callisto is one of the satellites that's been sort of a bit ignored because it's, it doesn't have the pizzazz of having its own magnetic field. It doesn't have the astrobiological interest that Europa does. And it doesn't have the sort of showy volcanoes that Io has. But I find Callisto to be a very interesting body. It's got one of the oldest planetary surfaces in the solar system. One of the ways that we can get a measure of the age of a planetary surface is by counting the craters. And the idea there is if I've got some pristine, smooth body, pristine planetary surface, and I stick it in the solar system somewhere, and I say, well, on average, one meteor should hit the surface every year, creating one crater a year. Then if I count 1,000 craters on the surface, then that tells me that surface was renewed 1,000 years ago. And so you can do something similar by analyzing the statistics of the craters to age the surfaces. And Callisto is one of the oldest in the solar system. And there are just craters on top of craters on top of craters. You almost keep looking and you just keep finding them. So I think Callisto is very interesting. Callisto may also harbor one of these subsurface oceans as well underneath the ice, but the jury is out there. We don't quite have the data to be able to say for sure. And then just to say that this is also driven by interest in the other bodies in the solar system. So this question of habitability is not just purely at Jupiter, is also at Saturn. So particularly studies of Enceladus and Titan by Cassini have also sort of furthered this question of habitability. in the solar system, but also further afield. So there are people talking about the possibility of subsurface oceans at some of the satellites at Uranus. Triton is a very interesting body. So Triton at Neptune has all of these this evidence on the surface of these plumes of organic rich material that have emerged. These are Voyager images, and so Triton may harbor subsurface bodies of water. People talk about that at Pluto as well, and Charon. So there's lots. This is quite a sort of a general idea. Even Ceres and Vesta, people talk about subsurface bodies of water there. So just to wrap up here, what's the challenge for actually getting out to Jupiter and doing this mission? To my mind, one of the biggest challenges is the radiation environment around Jupiter. And I talked about this sort of analogy with a pulsar. This picture here is a ground-based picture of Jupiter. And it's been taken in radio waves from the Very Large Array in New Mexico. And what it's showing you is synchrotron emissions. And these are radio waves given off by electrons that are being sort of forced to change direction. And what you're actually seeing here are the radiation belts around Jupiter. You're seeing these extremely fast-moving electrons, just like we see in a pulsar, for example. Like we see very, very energetic electrons in the Crab Nebula. And these sort of makes it look like a bat, but these wings up here, these are some extra energetic electrons that shouldn't be there if this system wasn't being so strongly driven. So we've all got all these energetic electrons in this system, and energetic electrons, they don't care if you've built a metal shield around your spacecraft. They'll go straight through. So the skin of spacecraft is made of aluminium, and these energetic electrons go straight through. And so the problem there is they go straight through. They can electrically charge the internal parts of the spacecraft, and which can then short out. They can electrically arc between different parts, and that can fry different parts of the spacecraft. It's something that happens to Earth orbiting spacecraft. But also it causes damage to electrical components. And there's only so much of this damage that they can take before they basically die. And so we're talking about things like silicon chips, even small discrete components can be fried. They give you very, very strong background signals in your detectors, which means that you don't get as much information out of them. And so one of the ways that Juno managed to get around this is that they took all of the electronics and they put it in essentially a lead box. They put it in a lead safe, which is what it is. This is the electronics box. And then they winched it and put it in the middle of the spacecraft with all of the fuel tanks surrounding it. So they were using the fuel tanks as additional shielding. Whereas you look at a picture of Cassini being built and the fuel tanks are in the middle and you strap everything else on the outside. For Juno, they had to do it the opposite way around. But this causes a problem with our planetary protection issue. One of the things that's often done is that you say, I don't need to really sanitize all the internal surfaces in the spacecraft because all of this radiation will fry any bacteria on the way out to where I'm going. But if you're heavily shielding the insides of your spacecraft, you can't get that. So you need to do all sorts of complicated heat treatments and things like that on the ground, all very expensive stuff to heat treat the inside. And those are the problems that the engineers have been wrestling with to build JUICE. So I'm going to finish up there. Thank you all for listening. Thanks for the invitation. It's a shame I couldn't come and see you in person, but thank you very much. I hope you enjoyed it, and I'd be pleased to answer questions if there's time.
Fantastic. Thanks, Chris. I think Jupiter's one of the most interesting places because we've had so many missions to it. It's really cool seeing how the missions are extending our knowledge as we go through. If anybody's got any questions, I think Carolyn had one, and I've had a few as we've gone through. If anybody else wants to put any questions in the chat or come off mute, now's the time.
Can I ask a question, Kevin? It's Louise.
Go for it, Louise.
Mine's probably a very basic question. Sorry about that.
Okay.
When we see the like a solar mass ejection from the planets, are we just lucky that we just happen to have a camera facing the planet at that particular time, or do they stay in the atmosphere for a long time? Do we know?
When you talk about
the plumes from encephalitis,
Plumes,
you mean
yeah,
the volcanic
sort of from like
eruptions?
Okay, so
things like that. Yeah.
So when we have these plumes, so the volcanic eruptions on Io are more sort of episodic. You know, they you won't see one for a while, and then one will hit. So in some sense, yes, it's luck that you catch it, and actually they weren't expected on Voyager. It was someone was just paging through the pictures, and I believe they were looking at pictures that were actually designed for navigation rather than science, and they thought, what is that? And then they realized it was volcanic. So that's a really good question. Yeah, we don't know if we don't really know when one's going to go off, and so you've got to catch it. And so one of the things that people try and do is this: they say we can't just keep taking pictures of Io and then just look for all of them when we look for all of the volcanic eruptions when we get the information back. Let's try and do something on the spacecraft where it finds them itself, and then only sends a picture back when it's got one. But the ones at Enceladus, they are more or less continually going off. We don't quite understand how they're being produced in the first place, but they seem to sort of be fairly regular. And also, some of them seem to turn on and off at different times, but because they're all sort of clustered together, you only look at the same place, and then you're pretty much, yes, you're going to see one because they're all coming from the same spot. On Triton, it's my understanding that, I mean, that's just one or a couple of photos put together, but I've read quotes from people who analysed these pictures back in the day, and they say it's one of those things where you look at it, and as soon as you've seen one, you can't stop seeing them because they're everywhere.
There's a bit like geysers
yes,
where they whatever the mechanism that's causing them to go off.
Yeah, there's a couple of
periodicity.
Triton, there's a couple of different theories about what's producing them, but we don't have. I think there is a front runner, but it's by no means settled at all. And there's some evidence for plume activity at Europa. You might have seen pictures from Hubble where they're seeing oxygen in space, looking like it's extending out of Europa. But it's fair. I wouldn't say it was contentious, but it's disputed, and people are trying to figure out whether they're real or not.
Thank you.
I had a question about Europa. I was a bit gutted that you've only got 2 passes. Is this because NASA was originally going to do it and pulled out, and you couldn't quite make up after that?
It's so that's part of it. There's part of it because of the number of because of the fuel requirements to engineer those flybys. You know, so we've got to burn some fuel in order to put us on a trajectory that will take us past Europa. It's also the amount of radiation damage we would accumulate on those flybys. You know, I've seen plots of the radiation, the accumulated radiation dose with time, and they are quite dramatic increases every time you fly past Europa. So it's a balance between saying can't not really go there and not fly past Europa, but our real focus is Ganymede, and we want to live long enough to be able to do the science at Ganymede. So it's a trade-off between saying yes, we would like more, but we would have to sacrifice power or mission longevity elsewhere. And that's always the case with this sort of mission design, is you're always having to trade one thing for something else.
So can you just confirm again the main attraction of Ganymede compared to the others?
Compared to the others?
Yeah.
I think one is the fact that it has this magnetic field.
Right.
giving you this sort of rich interaction with the rest of the system. I suspect that if push came to shove, that they said, we can, if you really want to, we can go around orbit. We can go into orbit around Europa instead. Everyone will go, let's go to Europa. but you know, the fact of the matter is that it's extremely challenging, and challenging not just technically, but that basically drives up cost, and so you won't be able to afford to do it. Yeah. So your sort of next interesting thing is Ganymede.
Right. Thank you.
And there is also a stronger case at Ganymede for a subsurface ocean. And so people are interested in the fact that I've got this subsurface. The way we find this, one of the pieces of evidence for the subsurface ocean, is that we saw the effect. We saw the effect of it at Europa in the magnetic field around the planet. So we know that ocean is salty. And we know that it's salty because we see the signature in the magnetic field around the satellite. So what's happening is you've got this Jupiter's sort of magnetic field is sort of flapping around across the satellite. So every time Jupiter rotates, you get this sort of flapping motion of the magnetic field over Europa. And so because you've got salt water in the inside, which is an electrical conductor, when you've got that moving magnetic field around the satellite, it tries to stop it producing an electrical current through this ocean. And that produces its own magnetic field, and we measured that. And so you've got a sort of an interesting configuration there. And this is something, you know, this is something that you see at the moon, for example. You see it in the response of the Earth's oceans. So it's a well understood phenomenon. But at Ganymede, you've got multiple things superimposed on top of each other. You've got this global bar magnet. You've got this ocean underneath, which might be responding to the variations in Jupiter's magnetic field. So you've got sort of like a layered situation.
Thank you.
Does the recent phosphine discovery on Venus change some of the mission parameters? I knew you. I guess that's a question that's coming up quite a lot at the moment.
I think I'm a little bit more reserved about that. I don't think it's changed the mission parameters. I think it's one of those things that does sort of extend your notions a bit. You know, you can talk about Venus being too hot, but you know there are thermophilic bacteria on Earth. There, you know, what's to say that there isn't a bacterium that eats sulfuric acid and can survive in really hot temperatures close to the sun? You know, we don't know those limits, and this is part of that journey. Is we're exploring those limits, and you know those limits exist closer to the sun, and they exist far away from the sun as well. So I think it just extends that idea, that sort of that Goldilocks idea that served us well for a while. But I think, you know, it's ultimately sort of stops you looking in interesting places.
No, yeah, I was more thinking that if you found phosgene in some, I assume that the atmospheres on the Jupiter moons are so thin that you wouldn't necessarily be able to detect it with Earth-bound probes. But once you're in orbit around these worlds, you've got a better chance of being able to detect things like that.
I mean, it's possible, yeah, it's possible. My understanding of the phosphine thing is that there are sort of a zoo of reactions that can produce it,
yeah.
And you know, from raw ingredients, if you like. And I'm not sure that those raw ingredients exist in the atmospheres of Ganymede and Europa and co. I don't know that for sure, but that might be the case.
Weird science of Jupiter.
Yeah.
You mentioned also that some of the previous satellite probes used nuclear power, and yet the most recent ones have gone basically 100% solar. Is there a reason for that? Is it weight, or is it other characteristics of the flight profile?
There's a variety of reasons. One is that nuclear power, and I should be clear when I talk about nuclear power sources, I'm not talking about nuclear reactors. I'm talking about what these things, they're I sometimes call them nuclear batteries, and they do have the shape of a battery, and they basically contain pieces of radioactive material. The typical one is plutonium, and they're arranged in these cubes inside, and because they're undergoing radioactive decay so continuously, that each of those radioactive decays releases a little bit of energy, and so that these pieces of radioactive material stay warm. And so you've got something which is basically not cooling down; it's staying hot. And then you can take a device which converts the temperature difference between the inside of the battery, where it's really hot because of all the radioactive decay, and the outside of this device, which is cold because it's next to space, and so you've got a big temperature difference between the two, and that generates the electricity. But it went through a period of being quite deeply unpopular. The one mission that has launched recently with nuclear power was the Mars Curiosity rover. So you see photographs of it, and you look at the back of the rover, and there's something which looks like a white cylinder with some fins on it, and that's the power source. That's the nuclear power source there. But it's partly I think sort of political and environmental. Cassini had to go through a lot of challenges to get launched with nuclear power sources. There's, I believe I'm right in saying there was a legal challenge, and so NASA spent a lot of time looking to see if it could be done with solar. So there were sort of political pressures, and also the systems that were used to produce the plutonium were not had stopped operating, and so the stocks of plutonium were quite low, so they basically couldn't build these devices, and so it sort of almost forced a decision to try and do it with solar.
Again, it's just one of those things, because you always hear of the balance between power consumption and fuel versus the amount of instruments you can put on board, plus obviously the overall payload weight. So it's always solar panels are relatively lightweight in comparison, I suspect, as well.
One of the metrics you can use is how much power you get per kilogram.
Exactly.
And you know, they're not as dissimilar as you might think. These nuclear power sources are of order 100 kilograms, 50, 100 kilograms, something like that. But a solar array is about 1 kilogram per square meter. So, you know, as soon as you start needing something that is
90 by
50 square meters, it's tricky. Plus, the bigger it gets, the more tricky it is to sort of fold it up inside the launch vehicle and then deploy it once you're in space.
Yeah.
And the other problem with them is that the bigger they are and the further away from the spacecraft they are, the harder it is to turn the spacecraft around, because it's like the ice skates are extending their arm.
Yeah.
It's created a really large moment of inertia, so it's actually quite difficult to turn a spacecraft quickly, so that can limit the life of the spacecraft or put more demands on how much fuel you have to take, because you need to fire rockets for longer to give you a certain amount of rotation of the spacecraft. So there are trades.
Anyone got any other questions?
No, it's fascinating though, absolutely fascinating.
Otherwise, I've got a couple more.
Oh, go on then.
Yeah, keep going.
Obviously, with the failure to deploy the high gain antenna, that obviously had a knock-on consequence. The amount of data that they could hold before they essentially overwrote it. I assume JUICE will get around that with modern data storage capability, because we're talking about nearly 20 years since that was designed. So I assume you've got large capacity for local storage of data prior to transmission in JUICE.
And to be fair, Galileo also had. I don't think
Galileo was in gigabytes, I think.
Yeah. And yes, and it's that was solid state as well. But yeah, I mean they've all got onboard storage. Yeah, absolutely, they've all got onboard storage.
Not like the tape wheels of Voyager.
So there's a really nice picture of the tape deck from Mariner 4 that flew past Mars in 65. I think it's 65. And I spent my childhood with C90 cassettes with a pencil trying to get the tape back into the housing.
I think we all did that. I think we all did that, yes.
So it just fills me with terror that you would put a tape deck on a spacecraft.
Yep, absolutely.
But there's one of these. There's a photograph I've got it in another talk I do, where they've sort of opened up the cover, and it just like smooth. It's amazing. Well, but a testament to the engineering that you can build it and launch it and it works.
Absolutely. I mean, back then, the I want to call it 8-track, was a Mobius strip of magnetic recording. So it just literally looped forever. It was brilliant. You never had to turn the cassette over. It's fantastic. You also mentioned that Callisto was highly cratered, and Francis responded to my question around other surface activities wiping it clean. Is there a reason why Callisto hasn't had the surface wiped in the same way that the others have, given that it might have something underneath it? Because it seems a bit weird that that's the only one that's completely pockmarked, like the back of our moon, for instance.
I'm trying to remember the. I think I'm right in remembering that that internal ocean layer at Callisto might be deep, and also might be quite thin. On Europa, if you've only got an ice shell that's a few kilometers thick, an impact comes in, and you're really quite close to a liquid source there to erase that. So in comparison, Europa has a very young surface. There are only a couple of craters that you can usually see on Europa. So I think I'm right in saying that actually the surface is sufficiently far away from a large water reservoir to get rid of it. But I'm sorry. I'm sure there's another argument why it was so heavily cratered compared to the others.
I'm just thinking the image that you showed was almost like the backside of our moon. When you look at our front side of the moon, you've got the big mare fields where obviously there's been volcanic activity and it's smoothed it out with some pockmarks on top. Yeah. But on the backside, it looked almost the same. So it's quite interesting to see the comparisons there.
Yeah, so I mean that's my interest in it is how is why that difference, why that dichotomy between the two. That's my interest in it. I can't remember the exact argument to answer your question properly, but certainly it is absolutely. I agree. I don't believe that there is that activity on the surface to renew it, like there is at Europa, for example, and obviously at Io with all of.
Sweet. Are there any other comments or questions?
Can I ask a question, please?
Absolutely, Louise.
Yeah. Am I right in saying that you said that was it Ganymede is larger than Mercury? Is that
Yes,
what you
it
said?
is. Yep.
Yeah. So in the event that you were going to be looking at Mercury and not Mercury at Ganymede rather than Europa, which was where I always thought that people had said that was where there was most likely chance signs of life.
Yeah.
Does that mean then that Ganymede's going to come into the into the fore? We're going to start talking about Ganymede as being a place of special interest now, or do we just have to wait and see? We're just so far away from it that it's just never going to happen.
I think
and Europa, you said, was very high. Radiation, you said as well, didn't you? So I mean, that's another reason perhaps why it's a non-starter. Ganymede might not be a starter either, but
so I think, yeah, Ganymede is, I think the spotlight will always be on Europa. But I think it's worth bearing in mind that before Cassini went to Saturn, Enceladus was thought to be just a ball of ice. And I remember sort of science programs when I was a kid, not long after Voyager, talking about Enceladus being a frozen ball of ice. And look what we found at Enceladus at Saturn. So I think given how close we're going to get to Ganymede with JUICE, the orbits are very close. We're going to map the thing in real detail. This is the sort of thing where you start to measure, you start to be able to see that sort of plume activity regularly. The plume discovery at Enceladus was, to some extent, there's a measure of luck there. You happen to see a signature that tells you there might be something interesting in that particular part of them. There's something interesting near the south pole of that moon that makes you go look in more detail. I think we're going to be at Ganymede enough that we'll hopefully see those sorts of things. We'll start to see, is there a patch of the surface where we go over it and we see signatures of something coming up from the inside, or you start to detect really interesting molecules on the surface in particular patches, or you see spots on the surface that are warmer than their surroundings and things like that. If we can characterize properly the depth of the ocean at Ganymede, we might find that there are regions which are deeper and maybe closer to the surface. We start to characterize how and where radiation gets to the surface, so you can do a better guess of what chemistry is going on the surface. So I think there are probably lots of surprises in store at Ganymede, where I wouldn't say take the shine off Europa, but certainly reveal really interesting things that might tell us a lot about this question of habitability.
Right. Okay.
I hope that answers the question.
Yeah. Can I ask another question as well? Sorry.
Yeah, go for it.
So these moons that are going around Jupiter are in a very narrow band depth-wise. Is that correct? It's just a couple of miles or something like that. Do we think that they are bits of whatever it is that are around, that are forming the ring, or do we think it's something that's been thrown out of the planet, or something that's crashed in and bounced out of the planet, or why are there moons? Is it just the coagulation of the rocks that are there, and there's bound to be some.
Right.
Because it's got a lot of, it's got so many moons, hasn't it?
It's got, absolutely, yeah, absolutely. Because of the orbits of the irregular satellites, you know, and also what they look like, you can sort of trace them to particular groups of asteroids in the solar system. So you sort of have a sense of, oh, these satellites, these moons at Jupiter, they go around in really weird orbits, and they've all got the same color as these asteroids that we see over here in the solar system. That gives you that sort of sense. Oh, they're just captured ones of those. The Galilean satellites, I think I'm pretty sure that it's universally acknowledged that they formed from the same stuff that Jupiter formed from, you know, so that you can have a cloud of material, and in that cloud you sort of form a planet at the center, and then some moons can form from the surrounding debris around it. I don't think it's beyond the realms of possibility that there were very, very, you know, right at the beginning of the solar system, you know, there might be these things all pinging around, lots of them all pinging around the solar system, and some of them got grabbed by Jupiter. But I don't think I don't think it's contentious to say that they were probably formed around Jupiter at the same time from the same cloud of stuff. Similar to some of the, you know, some of the other satellites. I mean, where that, obviously we don't have a time machine and we can't go back 5 billion years and find out, but I don't see any strong evidence for the Galilean moons having come from elsewhere. I mean, the place where that's clearly different is Neptune, where, you know, you look at Neptune's planetary system and it's really different to elsewhere. You know, so we've got there's basic. I sometimes describe this as Proteus and Nereid they're just like the bricks that you find in the back garden when you buy a house. Right? It's just debris. And Triton goes around Neptune in an inclined orbit and the wrong way.
Yes.
And so it's almost universally acknowledged that Triton is captured, that it didn't form. So actually, Neptune, the idea of Neptune may have had a satellite system like Uranus or like Saturn, but actually it's not there anymore, because the capture of Triton by Neptune was so violent that it just either destroyed what was there or ejected what was there into orbit around the sun. You know, and maybe Triton, what we see as Triton is a sort of amalgam of the thing that was captured with some of the bits of the original satellites that it destroyed during its capture. You know, so there are clear markers at Neptune that this is not what was there originally, let's say. Whereas I don't really see the evidence for that at Jupiter. Now, Saturn might be a bit different. So there's a relatively new theory that that says if I've got a sort of a dense ring system around a planet, but at the outer edge of that ring system, if you start to form little blobs of material, so you start, you know, it's like a few bits of ring particles start sticking together, and pretty soon you've got something that's sort of, you know, kilometer-sized, moonlet-sized at the outer edge of the rings. As soon as you've started to form that, it can start to grow because it's now more massive than its surroundings. So it can start to attract other ring particles to it, and it can get bigger and bigger and bigger. And eventually it gets big enough that it starts to gravitationally interact with the ring that it's part of, the planetary ring that it's part of, and that acts to push it away. And so it's almost like the ring gives birth to a new moon, which might explain this sort of sequence of satellites, that all of these satellites, Rhea, Dione, Tethys, Enceladus, Mimas, and there are other smaller ones closer to the rings, but they were actually born from the ring material.
Mm.
but we don't see dense rings at Jupiter.
Right.
So there's there are various mechanisms for giving us the systems that we've got today. You know, like I said, I think it's uncontentious that these formed either with Jupiter at the same time, or were captured from the sort of billiard balls that were flying around the solar system. At Saturn, there might be a hybrid. Some of these might have formed around Saturn. Some might have been born out of the rings. At Uranus, some of these could have been born out of the rings as well. You know, Puck and Miranda. Miranda's weird. Miranda looks like it's inside out.
Mm.
It looks like something. It looks like something shattered a moon, and then you put the pieces back together in the wrong order.
Yeah.
And then Neptune's different yet. So I think that there are lots and lots of different ways of doing it. And the challenge is actually looking at each system and saying, well, how do we think these all got there in the way they are? Because you might what gave rise to the system at Jupiter might be different, or happened in a different order or something at Saturn. You know, maybe Titan was the only original satellite, like the Galilean satellites, and the rest of these were born out of the rings. But that's part of the puzzle that we try and put together with these missions, is to be able to get enough information to pose those questions in the first place, and then to say, well, what's the evidence for this, that, and the other?
Yeah. Yeah. Thank you.
Can I just ask you, if all the Galilean moons came from the same source, why have they got such different physical characteristics? I mean, I know Io has got the gravitational effects which make it do that and get volcanic, but why are the others so different as well?
It's a very good question. I mean, Io does stick out, absolutely. Yeah, I mean, I think, you know, there's some similarities. I see some similarities between Europa, Ganymede, and Callisto in terms of them having cores and a mantle, and then an ice layer on top. It could be that Io once had an ice layer, but it was subjected to such dramatic tidal effects that it basically boiled off.
Right.
And that's a possibility. I mean, the other possibility is that Io had a different origin.
Oh,
You
never know, do we?
So there's I mean, it's still you know, I'm not aware of the latest on the different origins there, but I don't see that those are beyond. I don't see it beyond possibility that Io had a different origin.
Thank you. Have we lost Kevin?
Nope, just coming off
There
mute.
he is.
Fantastic, Chris. I think Mary summed it up with it was a fantastic talk that was well understood.
Yeah.
So it was very well put together. I super enjoyed it because it reminded me of all the things I think of when somebody says going to Jupiter. If anybody, once again, Chris, thank you very much for coming and presenting. Hopefully, when it's launched and the first data comes back, we can have you back to tell us how it all went.
Yeah,
That'd be really cool. Our next meeting, and Chris, if you wanted to join, because it's most likely going to be Zoom, and all our speakers are always welcome, will be Ivan Baladri talking about galaxy populations and the colour of the universe.
Ooh.
So hopefully we'll find out how he's been getting on with all that stuff. Where's my Zoom meeting just disappeared to? There it is. Other than that, once again, I wish we could all clap because it's very difficult to show the appreciation when you're all virtual these days.
it is. Yeah, it is.
But thank you very much for your time, Chris. Much appreciated.
It's a pleasure.
And, hopefully we won't put a cat in 3 million years on when we crash into Ganymede, because that really would be quite humorous. to anybody else, obviously the committee's here if you need to get in touch with us. It's committee@woodhouse2.com. And with that, if there's no other questions, speak now or forever hold your peace. Once again, thanks, Chris. Thanks to all for
Pleasure.
listening.
Thank
It's been
you.
a great
Thanks for all the
talk.
questions.
Yep, we're good at that.
Thanks very much, Chris. That's brilliant.
Thank you.